Okay, cool. All right, welcome back everyone for the final session. This will be Girish and Leonid, and they'll be talking about scalable multi-node AI workloads using SDN Kubernetes networking.
Thanks, Aaron. Leonid, are you on the call? Okay. Leonid, do you want to get started?
Is he responding? I mean, he's promoted and everything, so he just has to unmute himself.
Leonid, can you unmute?
Can you hear me now? Okay, fantastic. Thanks.
Yeah, let's get started, Leonid.
Yeah, let's get started. All right, next slide, please. So first of all, thank you all for the opportunity for us to come and present one of our projects. Girish and myself represent NVIDIA SDN team. Basically, the team builds and operates accelerated SDN solutions for NVIDIA clouds. For the most part, we use a combination of open source software, primarily Kubernetes on the compute side, and OVS OVN on the networking side. And we also leverage hardware accelerations as much as we can, since our cloud workloads are extremely performance and security sensitive. And such combination is really the only way to deliver solutions at reasonable cost. Multi-node AI infrastructure is a relatively new workload for us. So the question was whether we can use the same combination of OVS OVN software and our hardware that we've been using in production for quite a while and achieve the same results for extremely demanding multi-node workloads. The short answer so far is yes. Of course, today multi-node is primarily being run on either HPC-style deployments or tier one CSP deployments when there are proprietary solutions, and such kind of buy options do not go away. But at the same time, our conclusion to date is that basically leveraging open source, primarily OVS OVN, is a great option for such infrastructure. Is totally doable. It is worth investing in. And if you're in the similar boat, looking for a solution similar to ours, then this talk is for you. Next slide, please, Girish. One of the interesting observations or other facts on the infrastructure side is that essentially we are in the era of compute still being accelerated in terms of requirements, and demand is being met increasingly by accelerated compute rather than traditional CPUs. So this is really not a discussion anymore. Success of NVIDIA and other companies is really based on accelerated compute, and HPC and similar applications, including multi-node AI, as well as inference, essentially is driven by such accelerated compute rise. And networking is not an exception. It is a very similar trend. And over the history of networking, we used to see essentially cycles. Ethernet speeds jump at some point from gigabit to 10 gigabit to 100 gigabit and so on. And at that point, we find ourselves in a fast network slow host scenario, and a lot of investment and efforts both on the hardware side and in the software, including open source software, goes towards accelerated networking. And then at some point, compute catches up and the level of interest and investment goes down, because compute basically solves not all the issues, but it is certainly possible to over-provision, at least for the bandwidth requirements, if not necessarily for low latency. But now we find ourselves in such a cycle of fast network slow host for a very, very extended period of time. And that basically makes investment into hardware acceleration much more worthwhile. And the same goes for the software as well, because now there is a certainty that such investment will be viable for extended period of time, rather than kind of going out of cycle and out of fashion. Next slide, please, Girish. Multi-node infrastructure for AI workloads, both training, which typically requires huge clusters, as well as inference, which is typically today still single node, but moving to multi-node. Essentially one of the most performance-oriented use cases. And historically it's been done again either on HPC-style deployments with proprietary fabric, InfiniBand, and before that Quadrix and Dolphin and other fabrics which are not in existence anymore. And right now it is being done increasingly on specialized proprietary hardware and proprietary software fabrics within tier one CSPs, and those are great options. But again, not for everybody, and there is increasing trend of building basically AI factories, so to speak, or similar deployments on-prem. And this is what, again, OVS, OVN, open software with the right hardware accelerators on the host side seem to be increasingly very, very good choice. And in addition to hardware from multiple vendors, primarily acceleration for open virtual switch, including primarily match action, but also overlays. Of course, OVN runs on Geneve, and this is very compute-intensive protocol. It has to be accelerated. And the same goes for security groups. Kubernetes networking policy is one of the main mechanisms, if not the main mechanism, to accelerate basically increasing security and isolation demands on the networking side. So all that is required, but also very amenable to hardware offload. And another key requirement for such deployments on the software side, primarily on the control plane for OVS, OVN, is the scale. And this is where we also see some very positive recent developments, starting with OVN interconnect, distributed control plane, primarily for Kubernetes deployments. So this is also development that makes such infrastructure for multi-node deployments very, very practical. Next slide, please. And then the final ingredient, so let's say we've got our host side in order, we have accelerated compute, we have very scalable and optimized OVS OVN control plane, orchestration plane for Kubernetes. The last ingredient that also has been missing until relatively recently is support for Ethernet fabric, which is suitable for essentially performance results comparable to HPC and proprietary fabrics. Again, till very recently, things like essentially elephant flows collision made utilization in fabric and Ethernet fabric less than optimal to the tune of 60%. And with some recent advances in both RDMA fabrics as well as Ultra Ethernet, which is kind of new multi-vendor effort to create Ethernet, which is as performant as supercompute deployments, the utilization on the fabric goes to close to 100%. So again, the short summary is that now we have all the ingredients, we have hardware accelerator solutions from multiple vendors on the host side, we have highly optimized OVS OVN control plane, integrated with Kubernetes as a dominant orchestration platform for compute. And we have fabric, Ethernet fabric, which is very, very competitive with proprietary backend east-west fabrics of the past. And all that makes essentially such open source and commercial off-the-shelf hardware solutions for multi-node workloads doable and very amenable to further collaboration in the project and investment going forward. And at this point, I'm going to pass it to Girish to dive into details of the implementation.
Thank you, Leonid. We're going to have quite a few slides, so we kind of I'm going to rush through them. So the idea here is to kind of showcase the three things, right? On the node in a DC, what are we doing, right? The open source OSS stack on the node. The second thing is the network adapters on the node. And third thing is the fabric itself. So three things we're going to stitch together and in the context of deep learning trainings, right? Before that, I'll quickly go over what is deep learning training and why is inter-GPU communication very important. So imagine a image classifier neural network here, right? What we are trying to do is we're trying to train this image classifier. And we are training it by feeding it with the batches of 256 images. The dataset itself could have millions of images, but at any given time, we are feeding it with 256 images. And every 256 image, we try to see if the result is what we want what it is, right? If it's not close to what it is, we kind of go back through the neural network, fix the parameters, and that's called gradients, and then finally rerun for the next set of batches. So every set of 256 images, we're going to do the forward and backward pass, and this whole thing is, for an entire set, it's called an epoch, and actually they do thousands of runs against millions of images. If you have one GPU, and if you have to run this across millions of images, it will take years. So that's why they kind of end up running it on multiple GPUs. And there are various ways to do data parallelism. In this one use case, what's happening is that the same model is fed to each of the 4 GPUs here, and each GPU is fed with 256 images, unique 256 images, and each GPU will come up with its own local gradients, right? But GPU 234 does not know about GPU 1's local gradient, and same thing with other GPUs. So at this point, we have to take the local gradients from each of this GPU and push it to one of the GPU, where it will do a sum, right? It's called all reduce. And then it will push that sum to all the other GPUs. So at this point, all the 4 GPU knows about all the gradients and it has summed it. And then that becomes the global gradient, and it's again fed to the parameter, and new set of images are now trained. So how do we push this um, um, gradients that we locally computed at each GPU is through a library. One of the libraries called Nickel. It's called NVIDIA Collective Communication Library. So this is basically has a bunch of MPI function: all reduce, scatter, gather, one to all to one to many. So basically, it's all MPI collectives, and it kind of uses CUDA underneath, and that runs on NVIDIA GPUs. Um, if you have a node, Kubernetes node with 8 GPUs on it, these GPUs can be interconnected locally on the node through either PCIe or NVLink or shared memory, right? If these GPUs are on nodes across the data center, then you have to interconnect it through TCP socket or through InfiniBand or through any other networks that's out there, right? So um, now let's look at this is within the node. If you connect it through PCIe Gen 5, you get up to, so this is all bytes per second. So multiplied by 8, so you get up to like 200 bits per 200 gigabit per second in PCIe Gen 5. NVLink is a new form of interconnect that NVIDIA has, that it uses to interconnect the GPUs within the same node. And as you can see, that as a generation of NVLink we progress, as we kind of interconnect the GPUs within the same node at a higher bit rate. But now we are talking about hundreds of nodes, and each node having quite a bit of GPUs. Now we have to interconnect all these GPUs across the node. So therefore, networking comes into picture, and my rest of the talk is on this part of the thing, not within the node, okay? So in here, we are basically saying that if you're using TCP/IP socket to interconnect 2 nodes and then share this gradients across, you'll be soon bottlenecked by CPU because it's not offloaded. And here with 100 gig NIC, you maximum you're going to get about 80 gig. So right, because you're CPU bound. With RDMA, you're going to get up to 96, close to line rate. The thing is, these days, the nodes are equipped with more than 1 GPU. They might have 8 GPUs in it. And then obviously each GPU, if you have to interconnect, you need its own NIC. You cannot have one NIC for 8 GPUs, and the NIC will become a bottleneck. So the way it's designed is every GPU on a node will have its own NIC. If there are 8 GPUs, there'll be 8 NICs. And there will be 9th NIC for the host access, for the host management itself, okay? So let's look at the networking stack. The idea here is that if you have an AI data center with hundreds of nodes, each node with a GPU, and you want to enable multi-job, multi-tenant workloads, the only way to do it is in a secure, isolated, and predictable manner is to use OSS components, which is OVS, OVN, and Avan Kubernetes CNI at the top. And then, of course, we need matching hardware adapter to do a lot of offload. It's good to know Marvel, NVIDIA, and also vSwitch Semi, Dream, Big Semi also was here. So there are quite a few vendors out there who kind of working towards accelerating this whole OVS offload data path. So the idea is we have OVS on every node in the data center, then you have OVN on every node, and you have an Avan central piece. We still have not moved to Avan Kubernetes IC. This is from the point of Avan Kubernetes Central that waits out there. So we have OVS on every node, OVN control plane on every node plus the central component, and then we have Avan Kubernetes. Again, going with the naming inclusion discussion, it was called master before, so we're calling it as manager. So, and then we have one Kubernetes node here running on every node. So again, this particular slide is very familiar to everyone with our hardware offload enabled NICs like ConnectX. The first packet is missed, but the rest of them will be all offloaded to the hardware. So one thing I would like to call out here is that Avan Kubernetes CNI is the CNI that a lot of the developers in OVS and OVN kind of got together and wrote the CNI on top of OVN SDN control plane. Um, and basically, recently it was Sandbox. So we kind of got accepted as a CNC of Sandbox project, and that kind of gives us a lot of benefits. So what we do is in our Kubernetes CNI, every Kubernetes resource in the CNI, we map it to OVN resources. So the network policies kind of map to ACL support groups and other sets that Nadia and Dimitri was talking about in the earlier slide, earlier talk. And then these things are all native to Kubernetes, but in addition to that, we have extended Kubernetes to also work, basically every OVN awesomeness that's there, feature is there, we've exposed it to a Kubernetes custom resource. So we've taken the logical router policy and then converted it as an admin network policy so that we can do policy-based routing in Kubernetes. And then network cost is the feature that kind of is implemented on top of OVN QoS and meters. And then finally, packet mirroring, where I can ask for mirrored packets from a switch port using the OVN mirrors. So this is a logical topology. I'm not going to definitely go in detail about it. It's basically a 3-node Kubernetes cluster. Every node has a logical switch, which is connected to a distributed logical router, which in turn has a gateway router to kind of exit out onto the underlay and then to the internet. So all I'm trying to tell here is that for any CNI to call itself a CNI, it has to follow like around 7 to 8 tenants that's set aside by the Kubernetes networking. Like Kubernetes networking is very opinionated, and then they say we need to have like this 10 flows configured for any CNI to be called itself a CNI, and this logical topology helps us in fulfilling those 8 to 10 flows. Let's quickly look into DC physical networking here, right? And then try to see how we do things today and then where we want to be by early next year. So we have 2 Kubernetes nodes here, and each of the node has 8 GPUs. And the GPUs are internally connected by this vSwitch fabric through NVLink, right? And each GPU has a PF, right? And it has a PF, and then that connects to a leaf. So the idea here is that we want to keep the movement of the packet within the leaf switch. We don't want to go to spine, because if you keep everything within the leaf, then the routing is better. So that's the idea. So the idea here is that every GPU, the first GPU on every node, is connected out to the leaf 1, and then GPU 2 on every node is connected to leaf 2, and GPU 4 is connected to leaf 3. So if GPU 1 wants to talk to GPU 1 on every node to do that all reduce operation, it would all happen within the leaf node. If GPU 3 wants to connect to another GPU 3 on the data center, it will all happen on the leaf 2. Very rarely you want to go out of the spine. Of course, you will go out of the spine whenever when you have like a multiple of these structure called scalable unit. But regardless, let's say if GPU 1 here wants to talk to GPU 3 here, right? So what it would do is it would talk locally to the GPU 3 through this vSwitch, and from there it will take this PF through the leaf switch. So the first leg would be within the vSwitch here, and the second leg will be through the leaf switch. So this is called rail optimized network fabric, where each of the GPUs are all interconnected through their respective PF. Okay. How are people doing things today, right? What they're doing is they're using what is called as a multus. Multus is a CNI delegator. If you have a Kubernetes pod which needs multiple interfaces to it, you use what is called as multus, and the multus plugs the first interface to the pod, the second and third, and up to 8. Like in your case, we have 9, correct? So what they're all, at least in NVIDIA right now, what they're doing is the primary CNI could be any CNI. It could be Calico, Kubernetes CNI. For the secondary, they're just using pass-through. They take the PF and they pass through the entire PF into the Kubernetes pod, and then they plumb an IP on that PF, and that IP is an underlay IP. So in that way, they're kind of totally by just passing through the PF directly into the pod and using an underlay IP on it, we lose the complete ability to apply Kubernetes network policies on the second, third, fourth interface. We cannot do QoS on that. So it becomes very hard now to enable the data center for multi-job, multi-tenant use cases, because those 8 interfaces into the pod is now done through SRV CNI when it does not have constructs like OVN. So the idea here is that we create a bunch of logical switches, layer 2 logical switch, one per rail, right? If we have 8 NICs here connected to 8 GPUs, we'll have 8 rails actually, and each of them is a layer 2 logical switch. And then on this logical switch, if there are 1,000 nodes, there'll be 1,000 logical switch ports on it. And we can now apply network costs, which uses OVN costs underneath. We can apply Kubernetes network policies, which will use Avan ACLs underneath it. Now I can restrict traffic going through this logical switch between these nodes. And this is kind of a deep dive into how things would look like on a Kubernetes node. So here, one of the node, right, you see that we've created an OVS bridge on each of this interface. And then we have an VTEP interface on top of each of the bridge, so that the packet sent from this VF1 through this VF will be tunneled over Geneve between these two, between VTEP1 here and then VTEP1 here, right? On this particular VTEP, the packet will be now tunneled using Geneve. Similarly, this VTEP2 to this VTEP2, it will be tunneled. In that way, we would have created, rails, like pure layer 2 rails. And then in the case of multi-tenancy, what we can now, because we have Kubernetes network policies and the Kubernetes costs, we can now make sure that a premier tenant, a tenant who's paying money to do training will have higher costs set so that their packets on the fabric is respected or preferred more compared to a tenant who's not paying, who's on the free tier, for example. And then also using Kubernetes network policies, we can make sure that multi-tenancy can be ensured. In another setting, what's going to happen here is that each tenant would have their own L2 layer logical switches, and then thereby they have their own isolation at the Geneve layer, and therefore they're secure, isolated, and they don't have to worry that tenant A or tenant B is kind of, speaking on each other or things like that. So in summary, all we wanted to tell today is that using the OSS stack, OVN, OVS, OVN, and Avan Kubernetes, anybody can run AI cloud infrastructure using off-the-shelf commodity switches and hardware with GPU on it. And if you want to accelerate, obviously, you would have to use any NIC vendors out there that's amenable for OVS offload. So with that, there are a bunch of references here if you're interested in knowing deep learning and how we use Nickel for inter-GPU communication. Yeah, if there are any questions, we're open for questions. And 40 seconds.
Are there any questions? Denise, are there any questions online? I actually have a question. It's not actually the networking side of it, but how much power does some of these servers draw? Like how much?
Yeah, I mean, it draws a whole lot for sure. Actually, as we all know, power is the next biggest thing after gold and oil. So I believe that day will come when people will ask, can you not use your electricity between 6 in the evening till 10, and we'll pay you money. So the homeowners can make money out of power now. So, but yeah, it consumes a lot of power.
Well, it really depends, right? There is a wide range of servers with GPUs, so your mileage will vary a lot, but it's definitely more than traditional compute.
Thanks a lot for the talk. I wondered if you talk about a multi-tenant system and you separate the communication using logical switches, but maybe have multiple tenants on a single node. Could you then use RDMA to read the memory of the other tenant, basically?
Right. So our smallest unit of allocation is a single node. There's no two tenant on the same node. In that way, we kind of overcome that issue. And actually, we last week in Salt Lake City, me and Surya, another co-maintainer of Avan Kubernetes, we presented on network costs, which kind of from the cloud gaming point of view, like if you have two gamers on the same node using the same GPU, we have network costs that's implemented through OVN costs, QoS, and we can set minimum bandwidth, maximum bandwidth, and DSCP marking, and then still manage multiple tenants on the same node. Go ahead.
So you mentioned Geneve between the to implement the Rails.
Right.
Do you also use IPsec?
See, that's a very good point. Yes, IPsec is something that we have in mind. Actually, OVS IPsec in OVN, Oven already supports IPsec through OVS IPsec. It's just that the offload is broken right now. There is more. So offload is broken. We're fixing it. Yes, IPsec is a way to make sure there is no a poisoning of LLM, which is a real thing. So people can poison your data and then make your model learn something incorrect. So we want to make sure that it's all secured and it's end-to-end IPsec. Yes.
Okay, thanks.
Cool. Sorry, I had to rush through the slides, but I mean, I'm open to questions after this talk. Thank you
Okay,
so
let's
much.
thank our speakers.